Good morning, my dear students. We continue our discussion with resolution and moving to absolute configuration and finally end up with the E and Z notation of double bonded compounds. Now we discuss two terms. They are racemization and resolution. These two terms are oppositely working terms. Racemization is the process by which a dextro or levorotatory optical isomer is converted to a racemic mixture. We know racemic mixtures are equimolar amount of dextro and levorotatory isomers which does not have any optical activity, or a racemic mixture does not exhibit optical rotation. And this process by which a dextro or levorotatory isomer is converted to a racemic mixture is called racemization. The racemization could be carried out by chemical methods, by heating, or by using impurities or catalysts, etc. For example, if we are heating tartaric acid in water, D and L tartaric acid will be converted to racemic mixture. The reverse phenomenon is called resolution. Resolution is the process by which an optically inactive racemic mixture is converted to optically active dextro and levorotatory isomer. That means in resolution we separate the dextro and levorotatory isomers into two different using different techniques like mechanical separation, biochemical separation, or chemical separation, so that optically active dextro or levo isomers were obtained. So, racemization is opposite to resolution and resolution is opposite to racemization. Take down. The three important resolution methods are mechanical separation, biochemical separation, and chemical separation. In mechanical separation, we are just using separating the D and L mixture by hand picking, because when we crystallize a racemic mixture, the dextro and levorotatory isomers have different crystalline shape. So, by using a magnifying glass, we could isolate dextro and levo from their well-defined crystalline form. This simple method of separating D and L isomer by converting them to well-defined crystalline structure is the mechanical separation. In biochemical separation, what we do is we use certain microorganisms, and these microorganisms decompose either dextro or levo form, so that the solution contains only either D or L form. For example, if we use certain bacteria, that bacteria only consume dextrorotatory sample or they only consume levorotatory sample. So when I place this bacteria on a racemic mixture, it consumes either D or L mixture, leaving one of the isomer there. This type is called biochemical separation. In chemical separation, this is the best method for resolution process. Here we use certain compounds so that compound particularly combine either with D or L isomer. You got it? I am adding a particular stereogenic compound to a racemic mixture, and this stereogenic compound only react either with dextro or with levo. That means the reaction is highly stereospecific and the resulting solution on fractional crystallization, one of the isomer will be separated out. This is the chemical separation. Take down. Now we discuss a very important topic called absolute configuration or R and S configuration, or it is usually called Can Ingold Prelog rule based configuration. Why we use this R and S configuration? Because we have to identify each enantiomeric pairs clearly to have their structures. For example, you have two shoes, left shoe and right shoe. So you label it as left and right shoe. When we take an enantiomer, we have to label them as object and its superimposable mirror image or non-superimposable mirror image. So we have to definitely identify which is the object and which is its non-superimposable mirror image. For this purpose, we use the R and S configuration, which is also called as absolute configuration. For example, you see here, in this particular molecule, I have an object A and I have image B. See, in the object A, their spatial arrangement is different. That means the placement of chlorine and CH3 group is entirely different from that of the mirror image. And we know these two are enantiomers and they exist as such. So now the problem is how we identify A and B and how we label A and B. Experimentally we could say A may be dextro, B may be levo. If A is levo, B is dextro. But we have to represent these molecules exactly as you represent left shoe and right shoe. And we know basically the structure of left shoe and right shoe is almost the same. So to label the enantiomers, we use Can Ingold Prelog rules and we say whether the molecule is rectus or sinister. That is the R and S configuration. Take down. It is easy to represent a molecule as R rectus or sinister S. For this R and S configuration or absolute configuration, we have to set certain rules. And we know for any enantiomer, there should be a asymmetric carbon atom. And we know asymmetric carbon atoms are carbon atom in which all the four substituents or four valencies are different atoms or group of atoms. So for a particular enantiomer, take an asymmetric carbon atom and identify all the four substituents. While identifying the substituents, we should give them the preference or priority. And this preference and priority basically depends upon their atomic number. For example, if a carbon atom which is asymmetric have chlorine, bromine, iodine and fluorine. Chlorine, bromine, iodine and fluorine. We know fluorine is having minimum atomic number, then chlorine, then bromine and finally iodine. That means we have to give the priority for these four, fluorine, chlorine, bromine and iodine, based on their atomic number. Here the highest atomic number is to iodine. So iodine get the first priority. Second largest atomic number is for bromine. So bromine get the second priority. Third highest atomic number is for chlorine. So chlorine gets the third priority. And the least atomic number is for fluorine. So fluorine is having the last or the fourth priority. So identify the atoms or group of atoms around the asymmetric carbon atom and give their priority based on their atomic number. Highest atomic number should get highest priority, while lowest atomic number should get lowest priority. The second rule is that keep the molecule in such a way that the least priority should be away from the viewer. We know for any asymmetric carbon atom, it should be tetrahedral shape, so that we should place the least prioritized group, that is the fourth priority group, away from our eyes, or it should fall behind the molecule, and move your eyes from the first priority to second priority to third priority to the least priority. If our eyes move in the clockwise direction, the molecule is labeled as R rectus. If our eye moves in the anti-clockwise direction, when we give the priority, it is the sinister. So, by assigning the four group with four priority, we just see the molecule, and if our eyes move from clockwise direction, it is rectus or labeled as R, and if our eyes moves in the anti-clockwise direction or counter-clockwise direction, it is designated as S. You got it? R and S rule is very simple, but we should be able to identify the four different groups, give their priority with highest atomic number having maximum priority, lowest atomic number having least priority. Place the molecule in such a way that the least priority is away from the viewer. Then view the molecule and check whether our eyes moves in anti-clockwise direction or eyes move in clockwise direction. Take down. For example, take this molecule. This is the molecule and we have asymmetric carbon atom here. See, in that asymmetric carbon atom, we have bromine, chlorine, hydrogen and carbon of methyl group. So, the different atoms attached to this carbon atom, that is the asymmetric carbon atom, are bromine, chlorine, hydrogen and carbon. We know bromine is having maximum atomic number. Hence, the first priority is to bromine. Chlorine is having the second highest atomic number. Hence, the second priority is to chlorine. After chlorine, we have carbon atom, atomic number 6, which is the third highest priority. So, the third priority is to carbon. And the atomic number of hydrogen is 1 and it is having the fourth or the least priority. So, for this molecule, we have assigned the priority bromine, chlorine, carbon and hydrogen. Now see here, rotate this molecule in such a way that the least priority, that is the hydrogen atom, is away from us. That is represented by dash arrows. So hydrogen is away from us. Now see how our eyes is moving. Our eyes is moving from first priority, that is bromine, to the second priority, that is chlorine, to the third priority, that is the carbon. So our eyes moves in a clockwise direction. Clockwise direction. Hence, this molecule is labeled as rectus or R isomer. R isomer. You got it? Now take the case of B. For molecule B, the atoms or group of atoms attached are same. Bromine, chlorine, carbon and hydrogen. And the priority is same. Highest priority is bromine, then to chlorine, then to carbon. But see their spatial arrangement. A and B are optical isomers which are connected as object to mirror image. That means they are enantiomers. So when I consider the second enantiomer, the highest priority is to bromine. I am placing hydrogen away from the viewer and the second priority is chlorine and the third priority is carbon. So our eyes moves from first priority, second priority to third priority. Check again. First priority bromine, second priority chlorine, third priority carbon. And our eyes move in a anti-clockwise direction. You got it? Hence this isomer is labeled as sinister or S isomer. This labeling is called R and S configuration or absolute configuration. Take down. Now take this example. See here, I have a molecule here. This is the asymmetric carbon atom. In that asymmetric carbon atom, we have bromine, carbon, oxygen and hydrogen. The highest atomic number is to bromine, that is having the maximum priority. Second highest atomic number is oxygen. Third is carbon and least is hydrogen. So this is the three-dimensional picture of that particular molecule. See here. I assign the priority. Bromine with highest atomic number, maximum priority. Hydrogen with minimum atomic number, minimum priority or fourth priority. Now when I am moving this molecule, our eyes moves from bromine to oxygen to carbon. Bromine to oxygen to carbon. That is in the clockwise direction. Clockwise direction. Hence, this molecule is designated as rectus or R isomer. Rectus or R isomer. You got it? Now take this example. In this example, this is the asymmetric carbon atom and we have nitrogen, chlorine, carbon, hydrogen. Nitrogen, chlorine, carbon, hydrogen. The highest priority is to chlorine. Second priority is to nitrogen. Third priority is to carbon. So our eyes moves from chlorine, nitrogen to carbon in the anti-clockwise direction. Hence this molecule is a sinister or S isomer. S isomer. You got it? Take down. Now we move to cis and trans isomer. We know cis and trans isomers are represented to double bonded compounds. Double bonded compounds. If any compound is having carbon-carbon double bond, if the same atoms or group of atoms are on the same side, it is called a cis isomer. And if the same atoms or group of atoms are on the opposite side, it is called trans isomer. So for geometrical isomerism, geometrical isomers are labeled as cis and trans isomers. This cis and trans isomerism is based if the atoms or group of atoms attached to the double bond are same. For example, if this molecule, we have two group of atoms are same, that is the methyl group, and here also we have the methyl group. So we could say the methyl group are on the same side. Hence it is a cis isomer. Here the methyl group are on the opposite side. Hence it is a trans isomer. That means for geometrical isomerism, the condition is that the molecule should have a double bond and the atoms or group of atoms attached should be same. But there are many molecules having carbon-carbon double bond, but they have different atoms or group of atoms attached to them. To identify such double bonded compounds, we introduce a new notation called E and Z notation. So basically, if the atoms or group of atoms attached to a double bond are same, we could identify them as cis isomer or trans isomer. But for a double bonded compound, if all the four atoms are different, we use E and Z notation. E and Z notation. Take down. So to identify the E and Z isomer, we have to consider the corresponding carbon atoms around the double bond. For example, see here, I have a double bonded compound with 4 atoms attached to the carbon-carbon double bond. See here, one is bromine, another is chlorine, another is fluorine, and the fourth one is hydrogen. So I have to identify the priority of these 4 atoms: bromine, chlorine, hydrogen, and fluorine, because these 4 atoms are attached to the carbon-carbon double bond, and these 4 atoms are different. Hence, we cannot say they are cis or trans isomer. So we have to determine the priority. The priority is based on the atomic number. Highest atomic number atom gets highest priority. Here, bromine is having highest atomic number, hence maximum priority. The second priority is to chlorine atom, highest second atomic number. Third priority is to fluorine, and the least priority is to hydrogen. When I observe this molecule, bromine and chlorine have fourth and third priority, that is the highest priority, while fluorine and hydrogen is having the least priority, that is third and fourth priority. In this molecule, the highest priority are on one side, same side. See here, the highest priority are on the same side. Hence, it is designated as Z isomer. Z is called susamine isomer. How? If the highest priority are on the same side, or the lowest priorities are on the same side, it is called Z isomer. You got it? Take the second molecule, this molecule. The highest priority bromine and highest priority chlorine are in the opposite direction. Opposite direction. They are not in the same direction. Highest prioritized bromine is opposite to the second highest priority chlorine atom. That means they are in the opposite direction. If the highest priority are in the opposite direction, automatically the lowest priority are also in the opposite direction. Such isomers are called E isomer. E isomer. So we have Z isomer and E isomer. In Z isomer, the highest priorities are on the same side, while for E isomer, the highest priority are on the opposite side. You got the point? So to identify a double bonded carbonate compound as E endogen or susamine, we have to identify the priority first, and we have to see how the priority is placed, whether they are placed on the same side or in the opposite side. If the highest prioritized compounds or group of atoms are on the same side, it is called Z susamine isomer. If they are on the opposite side, it is called E endogen isomer. Take down. See here, the same thing. We are again representing higher, lower, lower, higher. The higher are on the opposite side. See here, higher in the opposite side, endogen. Higher on the same side, susamine. So, E isomer if the substituents are on the opposite side, Z isomer if they are on the same side. This is E and Z notation for double bonded compound. Now see this molecule. We have two molecules here. See, in the first molecule, we have the highest priority on the same side because the atomic number of carbon is greater than atomic number of hydrogen. So they are on the same side. So hence it is a zuzamine Z. Now take the second molecule. The second molecule, chlorine, atomic number highest. Here 3 carbon atoms are there. But for this carbon atom, there is another carbon atom attached to this one. So comparing to these 3 substituents, this is having 2 carbon atoms there. Hence it is having highest priority. They are on the opposite side. So it is an example for a E isomer. This is an E isomer, while this is the corresponding Z isomer. So if the priorities are on the same side, it is Z. If they are on the opposite side, it is E isomer. Take down.